Any question? Um, technically, analytic geometry is a different topic. In addition to linear algebra, not the same thing. Okay, so geometry algebra does calculations and geometry measurement. Okay, literally what the meaning of the word geometry. So last time we did dimension one, and so the current one is numbers. Okay, so if you know the two coordinates x prime of two points, then you subtract, take absolute value. That's your distance. Okay, now as we're moving on to dimension two, we're looking at the vertical and Cartesian system as supply. Okay, so then the vertical and horizontal directions taken separately have been solved. Okay, so we can just use that formula for horizontal and vertical distances. Okay, so that the problem literally solved, and not only on the axes, but also on every vertical and every horizontal line. Okay, so diagonal are have to be addressed separately. That is then addressed with the Pythagorean theorem, which is very much familiar. Right triangle, points A, B, and C, and the C is the longest one that faces the right angle. Then we have a squared plus b squared is equal to c squared. Okay, so literally the choice of rectangular coordinates, even though they don't have to be rectangular coordinates, hypothetically we can have a coordinate system like this, no trouble whatsoever, and the algebra will be the same. So that's the nice thing about same algebra, different geometry. Meaning different geometry is not that it is different in the sense of a different analytic. Put it on paper on which you're doing your geometry, Euclidean geometry. Okay, so then naturally the result should be the same. It's your choice to choose the grid that you like, and then the result should be the same. It is kind of just an analytic algebraic method of dealing with geometry. So analytic, but nonetheless the formulas will be different. Okay, so all not points the transfer that knowledge into knowledge would require would and knows what that the distance of I because comes so here on the other side next to term. Maybe cosine. 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 Has seen this before. Yeah. Okay, so the Pythagorean theorem failed. There's a theorem that takes care of that. It's called, can you guess what the name of the theorem is? You maybe have heard the name. The law of cosines. Anyone? So yeah, so it is possible anyway. So just to maybe bring something up later on. At this point, it is our choice to choose a Cartesian system, and with rectangular grid. Okay, so the Pythagorean theorem fully applies, and so this is a geometric theorem that is that is stated in the context of Euclidean geometry. So in other words, a piece of paper with a triangle drawn on it. If we were to now to move on to the actual Cartesian system, it is easy to think about not triangles but rather rectangles, and then we're not speaking necessarily of a triangle, a right triangle, but we're speaking of the diagonal of a rectangle. Okay, literally, as I suggested in the beginning, that the measurements in the horizontal directions are known, and now diagonally, with a rectangle, we need to know how to measure it. We don't have we're now okay, so that calculation is very straightforward, and that is our Pythagorean theorem, and it can be furthermore translated into the language of uh, and so we want to measure the distance. We could have 2 points, but no matter whether there is a Cartesian system or not, but I suppose we do have a Cartesian system. What do? We know the coordinates of the 2 points, and then for numbers to combine the four numbers to find to compute the distance, and we know once again how to the two things that we need is the horizontal distance and the vertical distance. So we go in horizontally to find get to the y-axis, to go vertically to go to the x-axis. We do the measurements. Okay, so this is what you see right here. You measure the distance in the horizontal direction, right, on the x-axis, right here. So this is what you measure on this side, and then on the other side you measure this. Okay, and then once again in the manner that we're already familiar with, and then in this case it's 3 and 4, and then just combine 3 and 4 together in the Pythagorean theorem formula, and we end up with 5. Okay, so we, in other words, we combine the distance formula for dimension 1 with the Pythagorean theorem and find the answer. But really, it is beneficial to do it once and just write the formula explicitly, even though I mean it is still the Pythagorean theorem hidden behind this formula. So it's still the same, looks slightly different, and because it is expressed in terms of the coordinates of the 2 points P and Q. Okay, so 4 numbers are combined together rather than 2, and but you probably should remember both of these. So, any questions about this formula? Okay. Okay. So there is a way, and that's very important point right now. Is transitional. We have to do it. Okay, so there was totality. So if you look at just it uncritically, you might think that the formula. So this is dimension 2, right? In dimension 1, it was x minus x prime absolute value. That was my distance. Okay, so and they do not look similar. Or you how do I get from number 1 to 2? We know how it did happen, but the two formulas do not look similar. Okay, but they actually do if we do it carefully. If we just what do I do now to actually see a match between the two formulas? They link very much in very revealing match. I square the formula. The first formula, if I square it, I will actually square both of them. Okay, so that way I will end up with this. Okay, so the square of the distance on the left for both of them. Okay, and then what I end up with on the right is the square of the difference over one variable, and the sum of the square of the differences for the two variables. Okay, so once again, the match, you can start seeing a pattern, I hope, of what's happening, what has happened, transition from 1 to 2, and if you do, okay, then you can guess what the next is going to be, and then the next and the next. So what's the next? What's the next line? Well, if you look at the first column, which says dimension, this is 1, then it is 2. What's next?
3.
3. Okay, so all right. So what about the other one? What's on the right? That's right. So can you be more specific?
Same as dimension 2, but it would add z derivative of z.
No, it's not a derivative. It's just a prime. It's just a derivative. Derivatives like this. Okay. Yeah, that's what you meant, I presume. And indeed, so just add an extra term with the third coordinate, and then you have your distance for dimension 3 right away. It's a guess, but it's a good guess. Once you see that pattern is developing, then you can have an educated guess made in order how we're going to compute the distances in high dimensions, including 3. But then, do we really stop? Do we start with 3? Can we do 4?
As far as you want, can't you?
Yeah, I mean, the only thing that's stopping us is from imagining what four-dimensional space is. But so once you start doing algebra, the algebra is it. So even if we cannot imagine, hypothetically, say we cannot imagine four-dimensional space, so what? The formula is there, right? So, and we do need the multi-dimensional spaces anyway for doing data analysis. So, which means that, yeah, we gotta need a formula. We have we need a distance somehow to make that space kind of a more real, even though we cannot visualize it. And we know we have the formula. We can produce formulas automatically, just adding an extra term. So as many dimensions you've got, there's many terms you've got in your distance formula, and so everything works out just fine. So like I said, then the important step is really not what the distance formula is in dimension 2, but rather how we got from 1 to 2. If we know how we got from 1 to 2, okay, so then we know how we will get from 2 to 3 and on, and then it becomes automatic. Okay, so just extra variable will produce an extra term, squared distance. Okay, so in dimension 1 and 2, the square of the distance is the sum of the squares of the differences of the coordinates. Verbal description of which applies to both formulas. Okay, and then once you do that, you can also realize it also applies to dimension 3. So literally now, this was also included, right? So the square of the distance is the sum of the squares of the differences of the coordinates. Okay, so one word, one sentence, pretty much rules them all, and no matter what the dimension is. Okay, so once again, this is a warning that that I might have brought up before, that the distances could be measured, even though both of them are distances, but if they're measured in different units, the formula breaks down. So if we speak of data, that's really, if you go in higher dimensions, you do not expect all the dimensions to be of the same nature. Because even when they are of the same nature, they are literally distances. Nonetheless, we do not combine them together with the Pythagorean theorem because it fails. You got to have over here in the formula for it to work. You have to have the same units, and you cannot add, well, feet squared to miles squared. That is simply not allowed. Okay, so adding two units without conversion is not allowed, and especially if you're doing data and you have miles and pounds, miles and pounds, then definitely you do not add them together in this manner. But nonetheless, we might have to do it anyway if we are once again in that kind of awkward situation. You have a bunch of data of very heterogeneous, and then you got to want to measure distances. So we'll look into that later. At this point, we'll just let's continue on. The topic, current topic, is geometry of dimension 2. Okay, so and we'll see how that works out in high dimensions. So okay, so we are transitioning from geometry of Euclid to geometry of Descartes. And in particular, we do not speak as much of triangles anymore, but we are speaking, for example, as you see what at the bottom is 3 points. And then we speak of the distance between the pairwise distances. And so there are 3 distances. So if they are located in a very precise way, and as a rectangle, then we have the Pythagorean theorem. If there is no Pythagorean theorem and we set aside the law of cosines, nonetheless, we can speak of the triangle inequality. Have you heard of the triangle inequality, right? The triangle inequality. That is the triangle inequality. Well, everybody knows it, just the name might escape you, but you see what the point is? The picture and the formula. Picture and this picture and this formula. Any comments? C is less than A plus B. That doesn't ring bell?
Would it be the length of one side is always going to be less than the combination of the other two?
Yeah, that's what it says. Yes. Do you see something in real life that you may have, encountered that related to this idea? We implicitly use it all the time. Anyone? So, okay, maybe if I name the, how about I put here A, B, and C? The points. I want to get from A to B. Okay, do I go straight or do I go first to C and then to B? Which one is better?
Probably just going straight.
Go straight. So it's a total common sense translated into mathematics. And so sometimes if you might forget where it comes from something that everybody knows. Straight line is the easiest, the shortest distance is if you go along a straight line. That's what it's saying. That's all it says. Okay, so mathematically we call it a triangle inequality. We put it in the form of for it applies to triangles, but also in addition to triangles, these points may happen to lie on the same line, which means that there is no triangle. That's what at the bottom there. But nonetheless, rule still applies. Except the inequality does not have to be strict anymore because C might be equal to A plus B, in which case. So the equality becomes non-strict, but nonetheless still works. And so so the point is that we want to make certain common sense things explicit in our development of the geometry of on the plane, so that we can move as we move on to higher dimensions. Some of the things that are the common sense might be forgotten, and then we want to put it in words and in formulas in the form of a theorem in order to then see if it makes sense to have it once we go to dimensions that we cannot visualize. Okay, so once again, I'm writing the triangle inequality, which is this. Once again, it is a Euclidean statement. I write it in terms of the distances without pointing out what the distance is. So the dpq now does not. We know what it states and what's behind it is the same formula as before this one, but nonetheless. There might be a different one. So we'll look into different formulas later, but for the time being, if we know how to measure or compute, it makes no difference, compute or measure the distance on the plane, then this inequality will always be true. So a distance between P and R is less than or equal to the sum of the distances from P to Q and from Q to between P and Q and between Q and R. Okay, less than or equal to. Not strictly because there's a possibility that lie on the same straight line that the picture on the right shows. Okay. So that's something for us to keep in mind. But once again, a straight line is the shortest, probably something that we should have started with because it is a common sense fact for everybody, and we just want to put it in writing as we kind of are being let's say pedantic here. Okay, so all right. So as you can see, it by the way follows from the triangle inequality. Also, you can at least for a right triangle, it follows from the Pythagorean theorem, right? Pythagorean theorem is, can I prove, which says that c squared is equal to a squared plus b squared, okay? And then I'm supposed to conclude that c is less than a plus b. Okay, so at the very least, it's really not much of an effort here, but if to prove this, you would have to understand algebra a little bit more than sometimes is the case, because you know, if you try to square a plus b squared, that's a common mistake, and so here you will not be able to make any progress unless you clearly understand that a plus b squared is not equal to a squared plus b squared. So that's the one way to actually make it kind of internalize the algebra. That's what you're not supposed to do with algebra without actually doing any algebra. That there is something behind it, and that's the Pythagorean theorem. Okay, so all right. So distance formula, triangle, midpoint. Now angles. Let's examine angles a little bit next. And so part of the analytic geometry we're only doing two. And the distances comes to mind first, but also the angles between lines. Okay, so once again, we start with dimension one, and then we will be talking about the angles between directions. Okay, so once again, just like with distances, we abandon triangles and rather in measurements. But rather speak of distances. Similarly, here we have to speak in terms of directions. Why directions? So well, here it is. If we, I said a minute ago, angle between lines. Okay, I have two lines. You see the problem with the idea of angle between lines. What is the problem? Yeah, there's ambiguity. What's ambiguity here?
Multiple angles.
There are four angles. Some of them are equal, but definitely these are equal, but these are not, and these are not. So there are two pairs of angles. So which one? Between lines, both of the answers are valid. Okay, so if we want to be specific, then it is a better idea to speak about directions, or in other words, vectors. Okay, so that's what we're aiming for dimension two, to speak of angles between vectors, or for dimension one, or direction. Directions is, once again, the line gives you two directions, and that's why it does not apply. But so between directions is a better way to describe it, and later on we will introduce vectors to make it even more specific. Okay, so so dimension one, how many directions do we have in dimension one? So how many are, so dimension one, how many directions? Almost two, right? That way and this way. So two directions. So either with the remember the line that we drew for the one-dimensional Cartesian system. It's a road with a chosen positive direction. That's step number one. Okay, so that's one direction we can go with. A positive direction, we can go with a negative direction. These are the only two possibilities. Okay, and then so we introduce vectors in order to capture that, even though, like I said, this is really trivial. It's literally trivial. There are two directions, and therefore, if we were to speak of the angles, there, how many possibilities do we have? We have two directions. So positive, positive, negative, negative, positive, negative, and negative, positive. Okay, so these are the four angles for us to examine. Okay, and we know that if it's positive, what's the angle? 0. Negative, negative is also 0. And then positive, negative, negative, positive, what's the angle? 180, correct. So in other words, the problem has been solved right away. You don't really have to worry about it in dimension one. Nonetheless, let's do it the hard way. Let's do it the hard way in dimension one, so that when we get to do it in dimension two, the hard way will not look as hard anymore. Okay, so vector in dimension one is nothing but a line segment of which we take into account, then the direction is hidden there. So we will also, it has a magnitude, not only the direction, but also the magnitude, which means that, by the way, that we are bringing in more and more stuff than we need for the problem that at hand. The problem at hand is the angle between directions, and the vector has not only the direction, it also has a has magnitude. Okay, but long term vectors are very productive, and they are a very nice idea. And so so vectors are in high dimensions. So anybody aware of what's the use of vectors beyond the directions? Why do we care about the magnitude too? Any specific phenomenon or concept that vectors represent? What? The physics, specifically forces of velocity. So not only in which direction you're moving or being pulled, for example, but also how hard. Okay, so we need it anyway. So, but it will be an extra effort for us to actually get rid of this stuff, because the angle does not depend on the magnitude, right? The direction does not depend on the magnitude, which means that when we measure in distances, or angles, as I did here, then the magnitude will have to be actually taken out of consideration. Okay. Anyway, so this is the direction. So magnitude is three direction positive. So at this point, I'm not even giving the direction any kind of numerical expression. Just say either one or the other. It's positive or negative, and the arrow points in one direction or the other direction, and that what creates a vector with both magnitude and the direction. As you can see, the magnitude is not. It is one over here. The magnitude is one, not negative one, because negative one, we don't need anything negative. Just like with distances, it is always positive or zero. Okay, so that's certainly is a zero vector for us to not to forget that the only one that have a zero magnitude and the direction is undefined. A very special vector. So once again, how do we compare? We just solve the problem, but let's do it in slightly harder a way. So once again, the endpoints of the vector could be both to the left of zero or both to the right of zero. Okay, so which means the directions are the same, and you can use that language for the time being. Just so imagine that you don't know anything about angles and never done any angles before, then you can still speak of directions in one-dimensional case, because there are two answers to the question. Is what's the angle between them, and the answer would be either you say they're the same or they are the opposite. That's a totally valid answer. Either the directions are the same or they are the opposite. So whenever the endpoints are on the same side of O, or the origin, or that in which case directions are the same, or they are on opposite sides, then the directions are opposite. Okay, so that's some observation that is worth noting, right? So PQ on this P and Q on the same side, and here PQ on opposite side of the origin. Okay. So which is, by the way, is opposite same side, means that both of them are either one negative, one positive, or both of them positive, both positive or both negative. Okay, so that's an example how we compute it. On the same side, on the opposite side. So on the same side, they have both of them are either on the positive or both of them negative. Okay, and here they are one positive, one negative. How do we detect that? And the answer is shown. Can you see it? How we can algebraically detect that they are on the same side or on the opposite sides in terms of the coordinates. So we're not looking at the picture P and Q, but rather we're looking at the coordinates. How can we tell very, very quickly that P and Q are on the same side or they are on the opposite sides? Well, that's one way, but it's kind of a less than algebraic way. The easy algebraic way is here. We multiply. So when you multiply two positive numbers, you have positive. When you multiply two negative numbers, you still have positive. Okay, so positive right here and positive. When they are on the opposite sides, it means that one of them is negative. When you multiply, you have negative. So that's how you can algebraically answer the question very easily about how do they have the same direction, they have opposite directions. And once again, when you multiply and you end up with positive number, means that the direction is the same. And when the that product is negative, the directions are opposite. Okay, like this. Okay. So once again, I'm doing it the hard way. We already have solved the problem. I'm doing it the hard way. Why? Because in anticipation of the when we're going to do this in the two-dimensional case, which is way more complicated. Okay, so we're solving the problem that has been solved already, but it is worthwhile to do a little bit more than seems to be necessary. So the product tells us the answer. This is the picture. So locations to the left, both to the right, same directions. The coordinates are either both positive, both negative. When you multiply, you end up with positive. Okay. When the directions are opposite, the coordinates are opposite signs, and therefore when you multiply, you have a negative. Okay, so once again, as you can see, the magnitude does not come into play, only the sign that comes out, and it tells us which way it is. So the directions from the origin to x and x prime not equal to 0, otherwise they are undefined, are the same when the product is positive and opposite when the product is negative. Okay. So once again, yet another illustration here, right here. So it is actually the sign. So another algebraic operation that algebraic function that we use very effectively it's called literally the sign, S-I-G-N, not sign, not S-I-N-E, but S-I-G-N, sign over there. So we only care whether it is 1 or negative 1. So the positivity and negativity is just captured by for a single number. And once again, either pointing in the opposite direction, same directions, and the angles as what I started with, the angles are either 0 or 180 degrees. There are no other options. So the match is now 1 is very straightforward. When that sign is 1, we have 0 degrees. When the sign is negative 1, it has 180 degrees. Okay, so let me put it in front of you. When it is 1, that's the first row. Then when it is 1, it's 0 degrees. When it's negative 1, it's 180 degrees. You must have seen this match before. There is a function that establishes this relation between them. 0 degrees gives you 1, 180 degrees gives you negative 1. What function is that? -180 degrees gives you negative 1, 0 degrees gives you 1. What function is that? What? Is there any, where if you're looking for that function, where are you looking for it? Among what kind of functions? Trig functions.
It's been a while. I'm gonna say sine.
Yeah, that is sine indeed. It is sine. Sine function indeed. Sine. I have it here somewhere. Yeah, that's my sine function. Well, it's actually cosine. I'm sorry. It is cosine. So they if we go this way, so when we this way, this is 0 degrees, and it is 1 over here. On the x coordinate, and if you go in the opposite direction, right here, so this 180 degrees, and it produces negative 1 on everything on the x coordinate. So that's cosine. Okay, so and yes, so that's what we're building towards, and even in one-dimensional case where everything is really simple, it does not have to be this complicated, but cosine will come up once we get to dimension 2, and we just, in anticipation of that, we recognize even in one-dimensional case, the angles are the only 2 angles to worry about, 0 and 180 degrees, but we know what we're going to end up with. We're going to end up with cosine. Okay, so and then the cosine of what? Cosine of, so this is my cosine. This is my cosine like this. This is cosine. Okay, 0 degrees gives me 1, 180 degrees gives me negative 1, and then there is a match whenever the the sign is 1, that means that the direction is the same and they're the opposite, and we can compute it very directly from one to the other and establish the angle, except in the opposite. It's going to be the inverse, as a matter of fact, right? So I'm actually starting. This is the starting point, and I have two coordinates, x and x prime. I multiply them, apply sign, and there are two possibilities: one, -1. In which case, what do? I'm doing the other way. What's the name of it? Cosine goes from right to left, and this one from left to right. What is it? What do we call it? No. The opposite direction. What?
It's not cosecant.
No,
Opposite cos.
no. Opposite. I'm intentionally not using the correct word. What's the correct? What? The inverse, right? The inverse. If we cosine goes from right to left, then what the function that we actually need is the cosine inverse or arc cosine. Okay, so not that we need it, but nonetheless, if we were to go all the way through two coordinates and we want to establish what the angle is, okay, so then that's exactly how it goes. So P and Q, then we get the coordinates x and prime, and then from that we carry out these computations: sine x times x prime. We end up with 1 or -1, and then we apply our cosine, and the answer is it's literal, not just we don't have to look up anywhere. It literally gives you either 0 degrees or 180. So the whole story is right there right now. Naturally, in dimension 2, it will be more complicated, but the story will be very similar in the sense that you're still gonna do some multiplication, okay, and then the cosine will also emerge. Okay, so but for the time being, that's we don't really need to worry about. Just this is the conclusion: is that multiplying the coordinates gives us the cosine of the angle. Okay. So that will continue on the plane in the two-dimensional case. Okay, so let's start with the two-dimensional case. How many directions do we have? Infinitely many. You can see how the problem has become by far more complicated. So once again, I'm not speaking of the magnitudes of vectors, only directions. And infinitely many directions can go in any direction you can think of. Fortunately, we already know that that's kind of a misleading. There are only two important directions, and that's the ones that follow the axes. Okay, so because the rest of the directions, and that's a big deal, become later. So only two matter. Only two matter. Why? Because the rest can be produced from those two, whatever that means for now. From those two, right? So if you know x and y direction, you're taking care of everything, just like we did with distances. Same with directions. Okay, so the two directions will give us the rest of the directions through algebra, right? So for example, we take care of this and we take care of that, and then what about this direction in 45 degrees? Well, you can just add them together. Okay, so add together x and y directions, and you give you the 45 direction in the diagonal. So how it works out exactly, we need to develop vector algebra, and so we will. But for the time being, let's just say that's just an anticipation. It's not really infinitely many directions. There are infinitely many, but fortunately we can control them by means of algebra. Okay, so I want to bring you back to pre-calculus, and before we get into more complex stuff about analytic geometry, just look at the slope. One way to measure angles has been, for in your experience, I presume, is just doing trigonometry, looking at the slopes. So a simpler kind of trigonometry, which gives you the slope of the line, and it is simply you look at it. It is tangent. So another trig function comes up, but it turns out to be not cosine, but rather, as you can see, it is the rise of the run. And so in this case, 4/2. That's how do I get the so also it's entirely in the spirit of we are pursuing here, spirit being analytic geometry. So something on a piece of paper, then with the grid added to it, you don't have to measure anymore. Let's compute, and indeed we can compute, right? So we have, if we have a line, we remember we want to angle between two arbitrary direction. In this case, it's not as good because it's one of them is a straight line. It is the x-axis. right? As you can see, this is the x-axis. So it's more narrow than what we want, but nonetheless, it is the problem is solvable very easily with the knowledge that we already have. You just if you need that angle alpha, what do? You incorporate and in fact think about it. It's if you have a piece of paper with those two drawn on it, it's entirely your choice to choose the grid that would follow one of those lines, and so the computation will be exactly like this, no problem. So anyway, you find the point PQ, and then the triangle is there. You can compute then the any trig functions can be computed, sine, cosine, or tangent. And the simplest one, as you can see, you don't have to worry about the Pythagorean theorem for the denominator, and for the hypotenuse, the tangent is the simplest one, right? And then it is, once again, we recognize it as a slope. And once again, it is the computation is very straightforward. So the only other problem might be what if we it doesn't give us all the possibilities. So the angles might be this way, that way, and then as you can see, there is no triangle. The triangle will be on the wrong side, So having on the right, it's on the left. So there is no exceptional direction in the case that we're trying to address, which means that any two lines, and we're supposed to just put it in the formula, those four numbers, put in the formula and get the answer, what the angle is. Okay, so once again, this is, as you can see, things change a little. If our point lies below the x-axis, then the computation is different, and the angle is different, even though it might look exactly the same, but actually it is negative. So it's going to be algebra. So okay, the tangent that I'm not sure you've seen, you worried about that before, but certainly it comes up in calculus. Remember this comes up in calculus. The slope is tangent. Okay, tangent, right? Tangent line, where it's come from. Or rather, right, vice versa. Right? Tangent stands for touch. Okay, rise over the run. What does it have to do with touch? And I just do not see how it goes. So I suddenly realized that it's unclear what comes first: tangent as the rise over the run, or tangent as we see it in calculus. Tangent as a tangent line, and the tangent as the function, and they are clearly related, but which one comes first really, I would have to look it up. Okay, tangent y over x, that's a straight line. So the problem is solved. It's just a limited problem. But what matters, we can still do sine and cosine as well for the same function, as long as we can compute the distance, which is even in the denominator. The distance from the Pythagorean theorem comes directly from there. If we are measuring with zero, the formula distance formula simplifies, and so that's what it looks like. So once again, the point xy, and we're measuring like this. We're measuring the angle between the x-axis and that line from O to P. Tangent, simplify, sine and cosine also simplify. Okay, so let's review some geometry, maybe a little bit, just to refresh your memory. Parallel lines, remember, we talked about that before, and now in the context of Cartesian system, we're not speaking of just lines drawn on the line, but rather they are now in their we can compare the slopes. Okay, so if intersection is with the x-axis, then the angles are exactly the ones that we just computed. So the slope is, in fact, it tells us if the two lines have the same slope, then something that we know, the lines are parallel. Same slope, parallel lines, or parallel lines, same slope. And so you can carry this out from computations. Once again, mx plus b, that familiar formula, point slope formula, rather slope line to set formula, written separately for two linear functions, and then for them to be parallel, the two slopes have to be equal to each other. So it solves the problem. Okay, so I don't want to go more into geometry, but certainly you can try to, based on the fact that that seems to be have been established that the slopes produce the same parallel lines, so you can try to prove that they don't intersect in the Cartesian system context, that the lines won't intersect. And the interesting thing about it, once again, we go to high dimensions, all of this will survive. Okay, it doesn't matter dimension 2, we are right now dimension 3 or dimension 4 or higher. It doesn't matter. You can still draw a line or imagine a line or two lines, and this such an idea as a line, a point, will still exist. Parallel lines still will exist. They will still not intersect unless you want to do a non-Euclidean geometry. Probably not. And then, so a lot of these things will still hold in high dimensions. In fact, they would call them Euclidean spaces. Euclidean spaces, dimension 1, 2, 3, 4, 5, or n. Okay, so all of them, they have the same Euclidean geometry. They're parallel lines don't intersect. Okay, so whether or not we can, there is no such a thing as a slope. That's what you will realize when we make that point. So dimension 2, 3, and so on. What is the meaning of the slope? So, well, dimension 2 still works. Let's say dimension 3 or higher. In dimension, as I just showed you, dimension 2 is the slope still works fine like this. But in dimension 3, okay, so imagine once again our physical space in a straight line. Even if the axes are drawn, where are the slopes? Okay, so then you have to sort of kind of find the relation of that line relative to the rest of the axis, and there will be slopes. There will be 3 slopes to worry about. So it's not an effective way of understanding directions in high dimensions, the slope settings, even though the formula is really simple. Okay, so parallel lines don't intersect. Okay, you can do it, prove it algebraically. Here's the proof. If the slopes are equal, then the 2 lines cannot intersect, and so that's another linear algebra problem to demonstrate. So whether we call them parallel or not, but if they have the same slope, they cannot intersect. We demonstrate that algebraically. So let's take a quick look. So same slope, M, and 2 intercept B and C. Okay, and then these are the 2 lines. Okay, and so it is the y and x are the variables. Okay, if they do intersect, there is a point that belongs to both of them. Okay, so I write these 2 as the variables, and so they vary, and they only become the same when we make a claim that I just did, that there is a point that have in common, which means that there are some specific choices of x and y that actually will satisfy both of the equations. Remember, what does it mean for a point xy to lie on this line? It means that when we plug it into the equation is satisfied. And now if the point belongs to both of them, you plug it into the first, it's satisfied. The second is also satisfied. Okay, so then in other words, it is the same x and y, and what we end up with here is in fact what we would say as we did before early on. Remember, it's a system of two equations and 2 unknowns. And so we ask ourselves, is it possible that does the system have a solution? And we say that there is, but how is it possible when M is the same? And if you read it, what's happened next, we subtract. Or we set them equal to each other, doesn't matter. These 2 are equal. Okay, Mx cancels out, and we end up with B equal to C. Okay, so what's the conclusion? We have 2 lines with the same slope. Okay, so but different y-intercepts, B and C. Okay, and then at the end we demonstrated that those 2 y-intercepts, B and C, are the same. So what's the conclusion? It's the same line, right? So then the idea that so the conclusion that is valid, then these 2 lines do not intersect. If they did, then it would be the same line. Okay, so two lines that are distinct cannot possibly have any points in common, and that's all. That's what we conclude. In a purely algebraic manner. The converse. Okay, so conversely, or the word that we, if you prefer conversely, vice versa, that's another way to do it. Yeah, vice versa. Okay, so if we have two parallel lines, they don't intersect. In the opposite direction we're going, you have two non-parallel lines, they do have to intersect. So how do we prove that? Two non-parallel lines intersect. How can we approach it? It works in exactly opposite way. So the proof that we just provided is no help whatsoever. Two non-parallel lines. Once again, but the shape they take is the same. So
We find a points of intersection.
right. Exactly right. So we write them, and then the effect should be the opposite of what we had here. We actually should be able to find it in the literal sense. We write the two equations, y equal mx plus b, and y is equal to nx plus c. As you can see, m and n now, the lines are not parallel, which means their slopes are different. M and N are different slopes, and now we're doing this kind of the same thing, but in the opposite direction. We do not assume, as we did here, that there is an intersection, then demonstrate that it cannot happen, but rather we're just trying to solve this equation with all the unspecified numbers. The only thing that is been set up is that m is not equal to n. Okay, but the rest is the same as before, and it is a system of two equations, linear equations, with respect to x and y, and so we just try to solve it. In other words, to find x and y, which is, geometrically speaking, is the point of that lies, point of intersection, lies in both of these two lines. So well, you can notice what happens. So these are the two equations, and then xy belongs to the intersection if it would satisfy both. We solve this equation, and this is what we discovered. Everything falls into place in the once we start solving it. Literally, what do we do with this? What's the first step to be made in solving the equation? How do you solve systems of equations? Elimination, substitution. So and there is not much substitution needs to be done because y is already expressed in terms of x. So let's just get rid of y, and we end up with one equation with respect to x. And then we find x, and then we substitute to find y. So that's pretty much every time the strategy is the same. So as you can see, mx plus b is equal to nx plus c, and then what we do. Oops, why do I not finish? Let's finish. Well, okay, let's finish here. So mx plus b is equal to nx plus c. Okay, so I pull everything, all x's to the left, and the rest to the right. Factor x out. And now something important happens. X is equal to what? That's right, but justified because what justifies this step? Why does it need to be justified? It would be zero, right? But we know that it is not because that was our assumption. The two lines are not parallel in different slopes, and so indeed justified by the fact that m is not equal to n. And then that's it. So we have found x, and then substitute into y. Y is equal to, well, it doesn't really matter. Mx plus b, x is substitute in here, and then we find we don't really care what that point is. We just want to be sure that there is one. And indeed, the two lines that with different slopes will necessarily have a solution. Means that they have a point in common. Means that the two lines do intersect. Okay. Okay, so mixtures, just once again, go back to the original problem of creating that blend of coffee. Once again, the problem that we solved this for this particular purpose, but the equation is slightly more complicated that we had, but they're by nature they're the same. So here we have x and y traditionally moved all to the left, and while terms without x or y they're left on the right. But these are the same equation that we have. So once again, these are the prices. The total weight should be 6 pounds, and the total price should be $14. Okay, so we could tell just by examination if we were just to ask our question: is there a solution there in the first place? Rather than trying to solve it, let's just examine it, and we realize that the slopes are different. Okay, and that's it. That's it. If we examine carefully these two equations, you realize that the slopes are not the same, which means that they must intersect, which means there will be a solution. Okay, that's it. On the other hand, then you can plot and confirm it, but really that's the full analysis. And this is a big deal in high dimensions. That question: is there an answer or there is no answer becomes more and more important. So especially, when we cannot solve the equation in the first place. We know that we can't solve this one because there are only two dimensions, but in higher dimensions, the solution becomes more harder and harder. So we got to know ahead of time whether or not solution might or might not exist in the first place. Okay. Okay, so back to the original problem. What is the meaning, or how to compute? Rather, the meaning is quite. The meaning of the angle between directions is more or less clear once we understand what the vectors are. But it is good thing to remember also that this concept is entirely applicable to high dimensions too, right? So between the angle between two vectors is understood, but is it lying on the plane or is it in space? It still makes perfect sense. And once you realize that, well, maybe these two vectors also lie in four-dimensional space. Can we compute the angle between them? Once again, it makes no difference. It's still valuable because this is two-dimensional. Okay, and Euclidean higher dimensional Euclidean spaces are simply made of lower dimensional Euclidean spaces, and so all the geometry is translated into high dimensions. So that's the good news. Okay, so let's just make clear what our vectors are. So we have then directions from O to P and from O to Q. The triangle emerges within Cartesian system. We supply with nothing but those four numbers, the coordinates of the points P and Q, and the problem that is solved already when Q is 1, 0. In other words, it's going along the x-axis. Okay, so but now not anymore. So the one of them was along the x-axis. That's not anymore. And so what we want to compute is this angle theta between OP and OQ. Once again, the OP and OQ lie on the Cartesian system, and there are two angles that we can compute as we already discussed. So both sine and cosine of these two angles can be computed. In this case, I write cosine but not sine for some reason, and sine too. Okay, so the angles with the x-axis have been found. Okay, so there is really no problem in that respect, but that's not the angle we care about. We need theta. Okay, so we know the angles of alpha and beta, and we need to find the angle of theta. So where are we heading with this? Find the angle theta from our knowledge of angles alpha and beta. Subtract, right? So what the question then becomes: what happens to sine cosine when we subtract them? And the answer is there is a formula. Okay, so the trigonometry is full of formulas, and that's one of them when you just like I said, subtract two angles. And we know they are sine and cosines. Okay, so what happens to the what will be sine or cosine of theta then? And the answer turns out that so the problem is solvable. Let's summarize. So the horizontal direction, we have yeah, so the angles for cosine, which refers to the projection on the horizontal. For the vertical is the sine. Okay, so which one we're going to need, we don't know. So we will be doing all four. Okay, so this is, so they have been computed. That's no trouble. And now theta is the difference. Well, yeah, keep in mind that indeed denominators looks complicated, but it's the same thing, nothing but distance formula. Okay, so our point happens to be either xy or x prime y prime, and it is the and we're measuring the distance from the origin. So that's what the denominator it comes from. It's the Pythagorean. So the difference is indeed theta is equal to alpha minus beta, and we know both sine and cosine are both alpha and beta, and which means that we can, there's a formula for it, of course. Here's the formula. This is the formula that trigonometry is full of, and so everything has been computed or figured out or ahead of time. So that's why we need both sine and cosine, because even though we only need cosine of theta, turns out we need both sine and cosine of alpha and beta, and so that's the formula. Okay, so we plug in then our prior computations. The prior computations are from the coordinates. So we do not want to speak of angles anymore. We want to speak of the coordinates, those four numbers x, y, x prime, y prime. And here they are. Okay, so we substitute them. At the end, this is the formula. A simplified formula, as it sounds paradoxical, but this is my angle, cosine theta. As promised, remember I promised in the beginning that the answer about the angles will be with cosine. And so not by accident, that's indeed we end up with cosine. Okay, so that's the formula is then the results here. It looks complicated, so let's simplify it. Let's try to simplify it. And as I said, the denominator is nothing but the product of two distances. And can you guess why the denominator contains these two quantities? They look kind of out of place, and why is it? Or why are they there in the first place? If you can guess.
I would assume it's some relation to distance.
Yeah, it is, but the more specifically in relation to the magnitude. To the magnitude of those vectors that we're going to talk more about. But the point is, remember, get rid of magnitude. The angle does not depend on the magnitude. So the fact that it's in the denominator doesn't make it dependent, but rather it is a cancellation. If you look at the numerator, it definitely also has something to do with the magnitude. So for example, if x and y, are become larger, right? The angle remains the same, but the magnitude increases. Okay, so how do we cancel it out? The answer should be independent of magnitude or magnitudes, two vectors, and that's what the role of the denominator. They serve to cancel the magnitudes. Okay, so that's an important idea. So, but nonetheless, we'll see how it cancels out. But the formula has been simplified quite a bit if you look at it. So, so trigonometry is hidden now. The denominator is nothing but the product of two distances. And the numerator it kind of looks weird, but it's not entirely what unheard of. We saw something very similar in the very beginning. Remember when we did multiplication in dimension 1, we had x times x prime. Remember x times x prime gave us depending on whether it's positive or negative, gave us the same direction or the opposite direction. So we are in a similar place as you can see, distances that cancel out, and the multiplication gives us the cosine of the angle. That's almost identically to what we had in dimension 1. Okay, so let's do vectors nonetheless. So this is okay, but not quite enough. We're gonna need vectors anyway, and so let's just introduce vectors. It's different from points. Okay, so they might seem similar, but it is once again a segment. Starting point is always the origin. Okay, so naturally then it is fully determined by the end point, which is P. And then that's all there is. As you can see, we do not speak separately of so that's all there is. That's the whole definition called a two-dimensional vector or two-vector, and then it is truly determined by the coordinates of the endpoint, which is written, however, differently. So P is AB in parentheses, and we use these triangular parentheses to write the vector. Okay, it's not written in stone, and the notation varies, but for the sake of this course, I want to distinguish between points and vectors. So you can actually write OP equal to AB with parentheses, but that would be might be a bit confusing. So let's keep them apart. And then as you can see, I do not speak specifically about neither direction nor magnitude. And why is that? The magnitude is easy to figure out. You can guess what's the magnitude of the vector. What's the magnitude of this vector? Well, no. What? How would you compute the magnitude of the vector that is defined in this manner? It's distance.
Pythagorean theorem, right?
Yeah, right. So it's distance. So the magnitude of the vector is simply the distance from the origin to the endpoint. That's all. What about the direction? How do we define direction? The answer is we do not. Okay, it's the other way around. It's not like we have vectors and now we understand what the directions are. It's the opposite. We understand directions by introducing vectors into discussion. Okay, so once again, AB, it's the same as P is AB whenever OP is AB. Okay, so the magnitude is nothing but the distance to the endpoint. Okay, from the origin. So it could be 0. Notation is, as you can see, these vertical lines. You can guess why the vertical lines. So can you see the notation here? The vertical lines right here. So vector with double vertical lines. What does it resemble? The vertical lines resemble what we saw just shortly a long time ago. It is a magnitude, yes. So remember what we used for magnitude in dimension 1.
Absolute value.
Absolute value. So that's supposed to resemble. So instead of having one straight line, we have two.
So with the third dimension, we have.
No, we'll stick with 2. That would be harsh to draw more and more lines. So it is two bars every time. So including with dimension 1. Okay, so and then the angle. Okay, so the bar. So this is the switch right here from the points, as what we have been doing from points to vectors. Can you see the difference? So there are arrows added to the story, and secondly, instead of distances, we now have the magnitudes, even though it's the same thing. The language is very important. Okay, I'll stop here. I'll see you next time.